we are back for another video, and in this video, you will learn about deriving the formula for geometric sequence. So let us consider this problem first. Suppose you have started to save 1 peso on the first day, 2 pesos on the second day, and 4 pesos on the third day, and each day after, you always double the amount of what you have saved on the previous day. So you are already familiar with this problem because we have used that same problem in our previous video. So let us have the same illustration for which it was stated on the situation that on the first day, we have saved 1 peso, while on the second day, we have saved 2 pesos, while on the third day, we have saved 4 pesos. But for each day after, we have to double the amount of the savings on the previous day. Since on the previous day, specifically the third day, we have saved an amount of 4 pesos, then we have to multiply this with 2 so that we get the next savings of 8 pesos. So, since you are already familiar with this, let us try to skip some parts in our list and let us proceed immediately on the ninth day. We will have a savings of 256 pesos, while on the 10th day, we will have it as 512. So let us try to use this same sequence on the derivation process. So let me have those information written as well here. Okay, now, so normally, we would like to have each of this term in the sequence be expressed in terms of the first term 1. So how we will do that? So let us have an expression for the second term that uses this number 1 that gives us an expression which is basically the same with this value of 2. So we can achieve such idea by having a 1 be added to 1 or having a 1 be multiplied with 2. Since you are already familiar with the concept of the geometric sequence, it is more about the multiplication process, so we must use this expression instead. And we would like to have our 4 as well be expressed in terms of the first term 1. So we may achieve that by having a 1 be multiplied with 4, but it doesn't make sense because we must also reflect what we have learned about the definition of geometric sequence, for which this number can be determined by using the preceding number and multiply a certain non-zero constant. So in this case, we can write the previous term as it is, but let us consider that it was already written as 1 times 2, so we will have our 2 be written as 1 times 2 as well, for which we can have this expression be equal to 4 by multiplying another 2. And on our fourth term, since we will be using the previous term of 4, and knowing that the 4 was already expressed in terms of 1 times 2 times 2, then we will be doing the same thing here. This would be our 4. And we know that the 4, when multiplied with 2, gives us this exact number 8. So since that we cannot easily do that here, then let us try to come up with a pattern that we can observe using the first 4 terms here. So let us start with the idea of representing this repeating numbers being multiplied to itself. And you have learned during the grade 9 that we can come up with an exponential expression which is an equivalent to such expression, just like this one. So let us concentrate on this one first. Okay. So we can have this be written in terms of exponential expression by writing the base, which means those same numbers being repeated in the multiplication process, for which the exponent tells us the number of those same multiplicants. So for you to realize the concept, then let us use this expression. So take note that we have those same numbers 2's being written as our base. Since there are three of these same numbers, then the exponent would be 3. And now let us simply have this be written like 1 times this. So let me use a dot to represent the multiplication process. So we have our 1 being multiplied to all of this. So this would be 1 times 2 raised to 3. So knowing that we would like to present the remaining terms of this, then let us have our 2 be multiplied with 1. So in this case, since we only have 1 of this number, then this would be raised to 1. Yes, it is normal that we do not have to show such exponent of 1, but allow me to write this 1 because we will be having comparisons later. So let us have this be expressed as the same expressions here, for which it includes a 2. So you also have learned on your grade 9 that any number being raised to 0 is equal to 1. So that when such 2 is being raised to 0, that gives us a 1. And we know that this one, when multiplied with that 1, it only gives us the same number 1. So they are practically the same. So that means we can do this. And now, the comparison that I have told you a while ago is to take a look at this numbers right here and take a look at how we will be able to come up with this number using such number. And you will notice that there is a certain pattern for all of those comparisons. So you might have already noticed that we can easily come up with this number by reducing the 1 by 1. And we can easily come up with this number by reducing the 2 by 1. Same goes for the rest. So 3 minus 1 is 2. 4 minus 1 is equal to 3. So that means we can also write that same expression for our ninth term, which is equal to 256, all the way down here, which is given by 1 times 2. So when our 9 is reduced by 1, then the 2 will be raised to 8. So same goes to 512. So 1 times 2. When the 10 was reduced by 1, it gives us the 9. Okay? And at this point, we would like to have the constants to be written in terms of general, or we will be using variables to represent all the constants that we have noticed on the expressions. Like this is obviously be our a sub 1. So that means all the 1 in our expressions will be changed to a sub 1. So in general, we have all of those be a sub 1s. While you have learned in the previous video that the number being multiplied to the preceding number to give us the next is what we call the common ratio. So the common ratio here is the 2. Again, the common ratio is usually presented as R. So let us change all the 2's with an R. And notice that we are only left with the exponents. So the exponents could be expressed in terms of the pattern that we have observed a while ago. So knowing that our n usually represents the position of the number or the position of the term in the sequence, having our first term, your n usually changes to 1, and on the second term, your n changes to 2, while on the third term, your n changes to 3. So all of this actually simply refers to n. So we will be changing all of those with an n. And since that our goal for this n be written to 0, so we have learned a while ago that we are simply reducing this by 1 to give us this exponent. And same goes for the rest. Okay, 3 minus 1, 4 minus 1, 9 minus 1, 9 minus 1 gives us 9. So that means the n will be reduced by 1. And you may notice that all of this 1, 2, 4, 8, 256, and 512 are merely reduced to the same expression. A sub 1 times r being raised to n minus 1. So that means that the nth formula for the geometric sequence is given by the expression a sub 1 times r being raised to n minus 1. So let us speak of this in general. A geometric sequence is a sequence where each new term after the first is obtained by multiplying the preceding term by a non-zero constant, which is r. So this is usually called the common ratio. If the first term of the sequence is a sub 1, then the geometric sequence is given by the following. So notice that we have arrived with this same expressions during the derivation process, where the a sub n is the nth term which is given by such formula that we have derived a while ago, which is a sub n is equal to a sub 1 or the first term times r, which is the common ratio being raised to n minus 1, where the common ratio is given by the formula r equals a sub n all over a sub n minus 1. So we can easily have the common ratio by using the second term being divided by the first term. And we will have more of this on the next video.